So we are assuming theta naught is the initial position, theta star is the final position, okay? The corresponding time instance is what? Corresponding time instance for this is T naught, and the corresponding time instance for this is T star. And that is what you're seeing here. Okay? You're integrating from time T naught to time T star. These are two time instances. Okay? And these are two true anomaly instances. Make sense? That is how you need to think about integration. See, essentially what you're trying to do is, you're trying to figure out if you integrate from this to this is a function, right? So if you integrate from this to this, you get the time taken or the angle covered. Okay? And that is what you're trying to relate out here. This is just substituted for H as mu A into 1 minus E square. Okay? You can find this expression if you want to know what is H. Your P is A square over mu, right? That is what we said. Remember? H is mu P root, right? P is what? A into 1 minus E square. So that is what you're seeing here. Okay. And mu A into 1 minus E square is actually something called mean motion. Okay. I'll tell you what mean motion is in just a minute. Now, this is your left hand side. Okay. The right hand side, how do you integrate this? See, this is how you integrate this. This is a fairly complex function, but you can find it in any standard integration book. Okay. So what we have done here is we have just integrated this on both sides. So this is the right hand side. Any questions, any doubts so far? No? You're all good? If you solve this, you're going to end up with this. If you solve this one, so you're going to, let's assume theta naught is 0, okay? And theta star is some theta. Can you assume theta naught equal to 0? No? Maybe? It is 0? See, theta naught, if your orbiting position is here, yeah, if the initial position is here, your theta naught could be 0, right? Wherever your initial position of the orbiting body is, you can assume that is the theta naught. So you can assume that theta naught is equal to 0 and theta star equal to some theta. Okay. Now if I compute this, it will be RHS is equal to E sine theta over E square minus 1 plus E cosine theta evaluated at 0 theta, okay, or theta star, minus 1 over E square minus 1 tangent inverse root of 1 minus E square tangent theta over 2 evaluated at 0 and theta star. This is actually theta over 2. So what you're going to end up is n over 1 minus E square 3 over 2 T star minus T. We're going to use capital T to represent T naught, okay? And I'll tell you what capital T means. There is a difference between T naught. It is, see, all capital T's can be T naught, but all T naughts cannot be capital T's. I'll explain to you what that means. Is equal to, what would this be? If you evaluate this at theta star, you're going to get E sine theta star over E square minus 1. This term would be 0, right? How would you evaluate an integral between two limits? How do you compute the integral between two limits? You remember? No? How? Huh? Right. So you do top minus bottom, right? The upper limit minus the lower limit. I'll give you what we end up with is something like this. This is equal to 1 over 1 minus b square into 3 over 2. Okay. Tangent inverse minus E sin f square root of 1 plus E cosine f. Okay. What is this term? Do you recognize this term? Right? Sorry, this is theta star. Okay. So this would be 2 over 1 minus b square 3 over 2 tangent inverse tangent of E over 2 minus E sin theta minus b square. What is tangent inverse of tangent? It's just the angle, okay? So it is E over 1 minus E square 3 over 2 minus E sin theta. So what you're seeing here is you see a relationship between time and eccentric anomaly. Okay. Now just pay a little bit of attention. I think I This is actually Gauss's equation. And this is Kepler's equation. Okay. From exam point of view, this is Gauss's equation. We did this last class, okay? That is Kepler's equation. From assignment point of view, from exam point of view, what you need to do, what you need to understand is, if you are given a problem in an orbit, how to translate that to Gauss's equation or Kepler's equation. All right? So if you are given E is equal to pi, where would the orbiting body be? If one of the E's is given to be pi, where would the orbiting body be? Huh? Orbiting body would be here, right? For E equal to pi, it has to be here. You think about it. If E equal to 0, capital E, I'm talking about capital E, it has to be here, right? So that is what you need to understand. If E equal to pi by 2, where would the orbiting body be? It would be at the top. You have to translate. What you need to do understand is, given the orbiting position, okay, how to calculate the time, how to calculate where it is going to be. All right, I will not expect you to understand the derivation. This or not understand. I would expect you to understand, but it will not be part of your exam for sure. You won't be given this in the exam. You may be asked to redo it for an assignment, but not for an exam. Now this T, it's the time of last periapsis passage. Okay, try to understand. Periapsis is, this is periapsis. Periapsis is the point of closest approach. Have you heard about supermoon? Supermoon? No? Supermoon. Yeah. It becomes really big, right? Why does it become so big? It is closest to the Earth. That is the closest point of approach. So this closest point of approach, any orbiting body, if it is not in a circular orbit, if it is an elliptical orbit, it's going to have closest point of approach and the farthest point of approach. The closest point of approach is called the periapsis. Okay? And the farthest point of approach is called the apoapsis. So you can take that. See, this is, if you want to initialize your time, every time it passes this periapsis, this is that T. This is that initial time. Okay? You know when this closest point is. So at that time, you set your clock. At that time, you make this T equal to T. And then you start propagating, or then you start figuring out, as at this time it was here, my theta was 0, okay? So as time approaches, at some other time t, what would my theta be? If you know your theta, you'll know where it is, okay? Any questions so far?